is the reason. And now the other thing is that we move on to a different kind of uh, algorithm altogether, which is known as clustering algorithm. And the clustering algorithm is a very simple kind of algorithm if you look at it. Not no mathematical, let's say, complications, but a very useful one, right? This is point number one, right? The second thing is this algorithm, which is known as clustering, is developed by computer scientists, right? Uh, and the because computer scientists have given it, uh, that is why like less of statistics is there, right? So that is one more thing that is like applicable here. So and to understand clustering, we have to first understand the notion of distances. It works on distances. If I have to group somebody, it's very, very simple. I have to understand the concept of distances. Then only I can group somebody, right? People who are very, very near can be grouped into a similar kind of a thing. People who are very far away cannot be grouped into a similar kind of group, right? That's a very, very simple idea. So clustering means there are basically two things that we need to understand, right? One, we need to find out something known as a distance, right? Somehow we need to find out a distance. The second thing that we need to find out is you have to find out is like, because this is a group, right? We are talking of a group. It's not about individuals. If I want to find out distance between two individual, things are very, very simple, isn't it? So but when it is a group, the group may comprise of, let's say, 50 people or 60 people, then which distance are we talking of, isn't it? Think of the group like this. So think of a group like which has 50 people in one group and there are 50 people in the other group, right? Now, or 60 people in the other group. So, and distance is a binary concept, always remember, right? Isn't it? Distance is between two entities. Now, they may be two objects, they may be two people, they may be two geographic locations, isn't it? So, the notion of distance is binary. Now, when we want to use it for a group, a concept is binary, but we want to use it for a notion for a group, then what do we do with it? How many distances are possible? My like throat is not all right, so probably you might be facing issues with the voice, right? So if you look at a group of 50 people and then if you look at a group of 60 people, then 50 into 60, that is 3000 kind of distances are possible, isn't it? Now which distance are we talking of? So what I'm saying is, before we go to clustering, there are three things we need to be clear of, right? One, what is this notion of distance? How does it play around in different situations? This is one, right? The first, so the objective of like before we start clustering, so pre-clustering objectives are: one, we very clearly understand the notion of distance, how it plays out into different let's say situations. That is one. The second thing is, are how many kinds of distances are possible, right? How do we understand them? How do we use them? That's the second thing. The third thing is, distance by nature is a binary concept. That means it is formulated to be used between two entities. Now these entities can be people, as I said, it can be geographic locations, it can be products, right? Marketing products, it can be anything, but it should be two entities. And now we are trying to, when we are doing clustering, as I said, clustering is about putting into some kind of groups. So when we want to do the grouping, then the notion of distance is used. So how are we using a binary concept on something which is group in nature, right? So that's what we need to be very, very clear about, right? So this is the pre-clustering kind of a thing. Let me give you a few examples. So that, and so the first portion, we are just talking of distances, that's all, nothing else. Okay, so clustering will come later. And there is a very nice paper by Harvey Abidi. And distance is a very let's say a very important fundamental machine learning concept, right? So we should have it very, very clear, very clear. I mean, we should be very clear about it. Half of the problems that I've seen in clustering, like Bhargavi in the second or first or second sessions, he was saying that also discuss things which should not be done, right? So definitely here, like in the end, I like to discuss clustering, or the way like people have defined distances. The fundamental problem comes in clustering, I tell you, is because people don't understand the notion of distances. That is the biggest problem, right? They define it like in different kind of ways. That's the basic problem. So this is one paper by Abidi. Harvey Abidi, I like him because I don't know if he's still a professor at University of Texas, Austin campus. And he writes things in a very, very simple way. So if you want to read something, he simplifies things, right? That's the good thing about him. This is one of the best simple papers that I found. After the end of the session, I'll pass it on to you, Harvey Abidi. But Harvey Abidi has also written papers on other things also, right? So there are other topics on which he has written. So I'll say that make a collection of his papers. He's one of the person who writes things in a very simple manner, very, very simple manner. That's why probably I like him, right? So when I was learning, typically in my days, when I was learning all these things, I mean, Harvey was like one of the good papers that helped me build my concepts, right? So collect as much as possible. Okay, so now let's discuss distances. I'll give you a few very quick use cases where which maybe probably or are based on distances only. So the first one is, there is a marketing manager, okay, and let's say it's about Bajaj, okay, and Bajaj wants to launch a bike which is 350 cc, right? And 350 cc, if you look at this high end, I'm talking of India, I'm not talking of the global market, because when I say high end, then the definition of high end will change depending on what country, what location you are, right? So in India, 350 cc is the higher end. So if you look at the 350 cc segments, it's heavily dominated by the Enfields, isn't it? Bullet, that's their brand. Now let they everybody, because this segment is already built, so there are many manufacturers who are trying to come into this segment, but natural. Okay, so let's say there is a marketing manager, product manager, you may call him. The marketing manager will come later on, but there is a product manager who wants to enter this segment, this 350 to less than 500 kind of a segment. Okay, he wants to enter this segment with a bike. So what will happen is, as soon as Bajaj launches the bike, the customers will start comparing it, isn't it? You also compare when you go and buy a bike or anything. You start comparing the features. You go to multiple dealers, cars also for that matter, and you compare. What about, let's say, the features in this, the length, width, wheel width, this and that, whatever, depending on how knowledgeable or how much you know about cars or bikes. Depending on that, your comparisons will start. And of course, budget is a very important constraint. Budget is a constraint, right? Always understand it's not a feature. You compare features and then put a constraint of the budget. This is how the decision making happens. Okay, so the simple thing is, how do we come to a conclusion, or how does a customer in the end come to a conclusion that two products are similar or they are not similar, isn't it? This is case number one. So let's say this assignment is given to you and you are supposed to develop an index saying that, okay, there is a model X which is launched by Bajaj, and there is a model 350 cc comes in, the 350 thing comes into different kind of formats you have seen in the Enfield thing, right? So simple bullet, and there are other models also. So how do you compare one model with the other model and declare that, okay, this is the similarity, okay, they are similar, something like this. This is one. When you look at the geographic notation, you see that Hyderabad is near to Bangalore, so their food habits would be bit closer as compared to Hyderabad and Delhi. The food habits would be different because we know the geographical distances between the two cities, between Hyderabad and Delhi, is larger than between Hyderabad and Bangalore. So finding some food similarities there, there is a chance, right? But Hyderabad and Delhi, there would be lesser similarities. I'm not saying they'll be totally different, but definitely there would be some differences. So this is the geographical distance that we have, right? And that there is one more interesting case, and a very, I don't know if I've discussed this case, ND Tiwari's case with you, right? But definitely, like, I like to discuss. So if you know, there is a very seasoned politician by the name of ND Tiwari. He was the chief minister of UP many times. So suddenly there was some person by the name of Shekhar who stood up from somewhere, God knows, and he claimed that he's actually the son of ND Tiwari, right? So then what happened is ND Tiwari, of course, I mean the politicians have a lot of money, and if you agree that he's your son, of course, and the son was not from the wife, so this can have many repercussions, isn't it? The image repercussion, the political, I mean, this can lead to political suicide. This is one, and second, the money has to be shared. Whatever wealth you have accumulated, that has to be so financial and image related repercussions. So of course, ND Tiwari said that I have nothing to do with him. So he went to the court, and the High Court very clearly said, ND Tiwari ji, no problem. If this person is lying, then we have rules which will take care of him. The only contribution that you have to do is donate 100 ml of blood. That's all. That's your contribution, and the rest we will take care. So the ND Tiwari ji refused to give 100 ml of blood, but then the court told the police to take as many policemen as possible, tie down Tiwari ji if required, and suck 100 ml of blood out of him. Right now, let's say, and then suddenly, I mean, Tiwari ji's memory came back, and he said, oh, I remember, Shekhar is my son. Some sorry son, I forgot you, and why don't you fight a election, right? So all that is there. Now leave that part, but the other part is this blood would have been taken to the forensic laboratory in Hyderabad. There only we have this facility of DNA matching, isn't it? So DNAs would have been matched. Typically, if you look at DNAs, then there are only 4 characters which are used, right? So how do you represent the DNA sequences? You will be surprised to know only 4 characters. That is what A, C, G, T. That's all, right? Only 4 characters are used. But a DNA sequence will have how many billions of these characters, right? ACGT. It would be a combination of billions long. It would be billions long, millions long, right? So there is one more action that, like, there is one more dimension that I'm bringing. So this string is 1 billion long, millions of long, right? Billion means you can 100 million is equal to a billion. So billion long characters. Uh, this area is a very big area. If you look at China, they are bullish on 2 areas these days. One is fintech, and the other is this gene mapping, right? Gene mapping is one more. They believe that the next revolution in the industry, that the next winner is going to be the gene mapping, and that's why they are investing very, very heavily in that, if you look at it, right? So that means when we talk of gene mapping, when we try to look at whether, if there are 2 blood samples, how do we establish they are like a father and a son, or a mother and a son, or 2 brothers, whatever it is, right? So how do you establish that? That is possible when we take 2 blood samples, and blood samples, if you look at it, this is some kind of a sequence you have, right? Billions of this. And so this is string 1, this is one string, and there is another string here, right? Which is also written like this only, T, T, C, G, a hell lot of characters out here, isn't it? How do you say that these 2 strings are similar and they belong to, probably, and these 2 people are blood related, or they are distant relatives, whatever it is, right? So the notion of distance is applicable in so many places. So these are the normal use cases. Other than use cases, if you ask me what are the applications in machine learning, then one, clustering is heavily dependent on this, right? So clustering is dependent on the notion of distances. Second, there is a wonderful technique, right? Very useful technique, I think, which is known as multidimensional scaling. We are not going to cover it. Why I'm mentioning this is I'll show you a lot of multidimensional scaling plots, but formally I'm not going to cover it because it's not a part of this. So also what I'm telling with this is that pick up this and start reading about it, because you know distances now. So definitely, like, MDS is something that you like to read. So try to prepare this area, try to read about MDS on your own, and if there are any issues, you can always discuss them. And the full form of MDS is multi-dimensional scaling, right? Again, a very useful technique. Why is this a useful technique? That we'll see. I'm not spending much time on this, just telling you the full form of it. And when we do clustering, you will come to know why this is a very, very useful technique, right? Sorry, dimensional, DI, this should be DI, dimensional scaling, right? So that's the full form. So that's one more technique where, like, the notion of distance plays a very, very important role, right? So straight away, the first thing that that we like to discuss is the distance is known by lot of names. One, you call it distances. This I've given you the name, and as I've been discussing with you, there are other names also. Distance is also known as similarities, right? If it is similarity, definitely it can be known as dissimilarities also, right? dissimilarities. So you can call it a dissimilarity also. When the distance is more, if you look at the different relation between them, if the distance goes up, then the similarities will always go down, isn't it? If the distance between two cities is large, then the chances of these two cities having a common kind of a culture in terms of food habits, in terms of so many other things, is going to be rare, isn't it? But dissimilarities will go up. This is one more word, and the fourth word that is used for this is proximity, isn't it? And proximity, generally you would have seen in context to relations, we use this term proximity, isn't it? We always say, okay, a son is more nearer to a father or mother, whatever. So there is a proximity, isn't it? This person is close to him or that, whatever. So that's known as proximity. So the notion of distances, these are four terms: distance, similarity, dissimilarity, and proximity. Generally you will see that these three terms are popular, right? These three terms are popular. And some people, if you go to them and discuss, they'll say, oh, distance and similarity and dissimilarity have a difference, right? So they might say that, but actually that's not the case. What happens is, distance is a numeric number, right? So you use some formula. We'll discuss some of the formulas. So use some of the formulas and you calculate distance, right? So some number will come. That's known as a distance. Similarity and dissimilarity are distances only, but they are scaled in such a way that they lie between 0 and 1, right? So I'm very clearly saying they lie between what? 0 and 1. So you scale it up. So when you scale it, then they become similarities and dissimilarities. So this is what some people may say, that okay, similarities are always between 0 and 1, and dissimilarity will always be 1 minus similarity. So the formula is dissimilarity equal to 1 minus similarity, or you can put it vice versa, right? So distances are pure play numbers, similarities and dissimilarities are scaled distances, and generally will lie between 0 and 1. That is what you have to keep in mind. Okay. And proximity is generally used in multidimensional scaling. At times we call it proximities also. So the four words are very, very near to each other, right? Also, when we are studying these distances, we'll study it in two parts, right? So let me mention that also. Distances can be two types. One, it can be a metric distance, right? A metric distance. Okay. So this is known as the metric distance. And the second kind of distance is known as the non-metric distance, right? Simply there is a non before metric. Okay. So non-metric. Okay, so we are starting distances, and as I said, that distances, and then of course the question, once we discuss distances, then the question will come. I discussed three objectives with you, and then the question will come, right? Why are we discussing distances in the context of clustering, isn't it? So metric distance would be used when your data is a ratio data. Always remember, right? So if your data is a ratio data, can we have examples of ratio data? Very simple thing. We always use these examples, right? It can be earnings in case of a financial thing, annual incomes, age, many other things that you can take, right? Generally when people do surveys, they use scales, right? Those are known as Likert scales. Okay, just to tell you, those are known as Likert scales. When people want to come out with new let's say products, they go with questionnaire. You would have also filled a lot of questionnaires, either online or offline, whatever, that's irrelevant, but they're Likert scales. So Likert scales generally would be on a scale of 1 to 5 generally, right? And they'll be like statements. Do you like this is the best product? So you'll be given a scale of 5, where 1 may mean you strongly disagree, 2 would be you disagree, 3 is a neutral position because you don't know about it, so neither can you agree nor can you disagree with that. 4 is you agree, and 5 is strongly disagree, right? So this is known as a Likert scale. Generally what happens is, Likert scale should be treated as a what kind of, it should not be treated like a ratio data, but what happens is, when you are collecting this data, it is easy to collect, but directly, if I say that this is ordinal kind of a data, then this will become categorical data, and categorical data by by nature is difficult to analyze, that we have discussed. So what people do is they say, because I have, the questionnaire is very long, and I am collecting lot of data from lot of people. So even if there is a categorical kind of a data, a discrete distribution will also convert into a let's say a continuous kind of a distribution. So this Likert data, people generally treat it like a ratio data. Okay, and there's a lot of debate around it. So I'm just telling you that there is a debate, and for simplicity people generally treat the Likert data as a ratio data. By chance, if you happen to handle this kind of a data for some of the client or something, right? So Likert data can be treated as a ratio data under certain conditions. Okay, but there has to be some conditions, then only you can treat it, right? So this is ratio data. So now if I treat like a data as a ratio data, my job becomes easy, isn't it? I can consider, I can why does my job become easy? I can find out people's choices, isn't it? When I'm launching products, it's very important to understand customer choices, isn't it? I need to model customer choices. So customer choice modeling is also one of the areas. Many techniques are used there for customer choice modeling. We're not getting into it. Some of them are very sophisticated, some of them are easy. Clustering, you can use, some people use a simple thing like logistic regression also for doing that. And then there are other very exotic methods also for doing something known as a customer choice modeling, but it's a area where in marketing which is like people do use. Okay, so in customer choice modeling, if you want to understand how similar people are based on their choices, then you can calculate the distance between them. This could be a very simple thing. So people who are very near would be have similar choices, and people who are far away will have a different kind of choices. They are dissimilar on choices, isn't it? That's very simple. Where is non-metric distance is used? They are used wherever you have string kind of a data, right? I gave you Tiwariji's example, right? So the NDA, so not the NDA but your DNA. So when your DNA has to be mapped, then these are known as string, right? Or it can be, let's say, a computer program converted into a binary thing, 1010, right? So let's say on the machine level codes are available to you, you don't have access to the higher level codes, right? So somebody used, let's say, COBOL, and those COBOL codes are not available to you, but they have been translated into a machine level code, and those are available. So how will you look? If you look at the codes, they'll be 1010 kind of a thing. And then somebody comes up and says my program is similar to the program, right? So how do you compare those? This that string of whole lot of 1010 would be there, again a very long string would be there, isn't it? So how do you compare those two strings and say that okay, they are similar in nature, isn't it? So that means when you look at distances depending on the data, right? So the data type is almost a very elementary thing, right? It's something which will come up every time. So if it is a ratio data, you can always use a metric distance. So and if it is a string kind of a data, always remember it, you can only use non-metric data. Please remember that, right? Now let me give you an example where you can go wrong, right? Let's say the data is like yes and no, right? Yes no kind of a data, binary data, and somebody says I've coded it, I've said yes is equal to 1, no equal to 2. This is what I do. Now because I've coded it 1 and 2, this is absolutely wrong. If you start using any of this distance, absolutely not allowed. This is completely wrong. Use something from here. That's the right way. Okay, this code is just a representation. I've told you many times. The nature of the data is string, or it is characters, you may say. It's a categorical data, string data, or let me put it categorical data, right? So this is categorical data. Then this distance has to be used, which is known as non-metric distance, right? This is one. Now let us take some examples. How many kinds of distance measures are there? At least I have come across more than 100. Now everything in machine learning is very big. You can see that nothing, we never talk about 2 or 3 or 4 or 5, never. Everything is 100, 150, I mean. And if you ask me like how many clustering methods themselves are available, around 200. 200 clustering algorithms are available in this world. So if you take a target to learn only clustering, all the clustering algorithms, probably it might take 10, 12 years, isn't it? So that's how I mean, it's a very, things are very spread when we are into machine learning. Okay. I mean, a bad part is that they are very spread, but the good part is, if you have a very specific kind of a problem, you can search for a very specific algorithm and probably solve it. That's the good part also. Okay. So it depends on how you look at it. Okay. So let's focus on distances. When I said distances are of 100 types, then can we have some examples? Okay, and then we'll get into the calculation part of it. Okay, so metric distance, I'm just quickly putting some example. And as I said, no way this is exhaustive, right? No way. I mean, if there are more than 100 metric, then probably giving just 4 or 5 examples probably doesn't serve every purpose, but the majority of the cases would be covered. So the very popular metric distances are Euclidean, right? Euclidean distance that all of you will know. Ninth or 10th, wherever, or 12th, you would have done some coordinate geometry. So there Euclidean distance would have been discussed. Euclidean, the most used kind of a thing. It's the potato of distances, if I can put it this way, right? So Euclidean distance, this is one. The second distance is a very interesting one. We give it many names. We call it the Manhattan distance. Manhattan is a place in New York, so named after that. So Manhattan, or you can call it the city block distance. This is also known as the city block distance, whatever name you will give it. Okay, there are two names to that. So city block distance. Okay, and then we have the third kind of a distance that probably is popular is Minkowski, right? Minkowski distance. So this is Minkowski, right? And the fourth one, so I'll only like to put four here. The fourth one that you see here is Mahalanobis. Mahalanobis distance is named after PC Mahalanobis, right? So PC Mahalanobis was the founding director of Indian Institute of Statistical Sciences, ISI as we call it, in Calcutta. uh, PC Mahalanobis, and he was the member of the first planning commission that was set up in India in 1930s, right? So the PC Mahalanobis. So that's a matter of pride for us Indians that he has given a distance. Not only this, I mean, I'm not telling you because this is given by an Indian, but there is much more to this. This is the only distance which is immune to outliers. The other distances are the distance measures are very prone to outliers, but this is one distance which is a very robust distance, immune to outliers. That's why if you have a data which has lot of outliers, I'll always say PC Mahalanobis or the Mahalanobis distance, sorry, would be the best distance to use, right? So it's one of the very robust distances to be used. Okay, so whenever like people have outlier kind of a data and they think removing outliers will reduce the data to a non-acceptable level, it's better that we prefer Mahalanobis distance, right? So this is there, and then the fifth one which you will come across is something known as Watt's d square. So the Watt's distance, Watt's d2, right? Some people call it Watt d2. That this stands for Watt's distance. That's, I don't know why this is called there this way, but Watt's d2, right? One thing interesting I'll tell you, this is the mother of all distances, right? This is the basic distance. And once you tweak this, it all results into either this. So if you tweak it, it will result into Euclidean, or it will result into Manhattan. And if you tweak Euclidean, it will result into Mahalanobis, right? And if you tweak Euclidean, then it can result into Watts also, right? So it's like a family. So some one distance came and then slowly gave rise to other things, right? So we are interested in five distances right now. As you go along, you can pick many of them. I'm just giving you some names, and I'll tell you like how they are calculated. That's so that you get an idea. Okay, how are they calculated? So if you look at non-metric distances, but it is absolutely important to understand and appreciate the notion of distances. And I told you the biggest blunder happens here. People just don't appreciate it, and they use. I've been surprised to see that people have used Euclidean for a categorical data kind of a thing, right? In my like company itself, I mean, somebody had done a very wonderful exercise. So this was the incidences. Like incidences means that if there is a software, people are trying to use it. There are a lot of software that companies use, right, for different purposes. I'm not talking of office related software, but softwares which are put on the company server. Example, CRM is an example, customer relationship management, or it may be a software to monitor some electronic devices which are functioning, anything. That there's so many softwares. So people go and try to use it. And if there is some problem, then what is going to happen is that that's known as an incident, right? That the login failed or the system crashed or something like this, right? So these incidences are generally, there would be a comment and these incidences are reported. Now there was huge data, millions of uh, entries here, and people were trying to form clusters out of it, right, last week. So what they did is they did a very intelligent thing. So this was like a small sentence. Think of it like a small sentence. So what they did is, to every word they gave a code, right? Code means the way like, yes, I give one, no, that was fine. But they devised a very, very genius kind of a scheme, and they said we'll give only prime numbers, right? All of you know what are prime numbers. Prime numbers are numbers which cannot be factorized. Example 1, 13, 47. These are all prime numbers. You can't factor them, right? One is only the one is the only factor that they have. For that matter, if you look, there are many prime numbers, 53. So they gave codes prime numbers. So I asked them like, why prime numbers? And they said that because what we are going to do is we are going to multiply these things, and we are going to multiply them. So prime numbers, when you multiply, you will get a prime number only, right? So that is the idea that they had. Now, I mean, this was an out of world kind of a thinking, isn't it? I mean, why should I give prime numbers and why will I multiply them and then use it in a clustering, right? So that's completely, I mean, too much out of the box. I think out of the world, and it's not out of the box thinking also. So that this was the problem. Should not have been done like this. Absolutely. Okay. So now coming to non-metric distances, what are the distances which are like popular here? So non-metric, the distances are Jacquard coefficient. They are generally known as coefficients, and some people, and they are similarities actually, and their values will always lie between 0 and 1. So you'll see their values generally lie between 0 and. So some people say non-metric is not the correct word. It's actually similarities. So whatever, I mean, people will say different kind of a things, but what I'm telling you is something like logical, right? So these values generally will lie between 0 and. So Jacquard coefficient, right? Then the most important for us, because we are going to use it very, very often, is something known as Gower's coefficient, right? GOWER, Gower. The methods of calculating them are given, right? We'll not go into the methods of calculation of each and every. Otherwise, what will happen? It will take a lot of time, right? And the main issue would be gone, and we'll be focusing on this. But what I request all of you is to, and these are very easy thing. I'm not telling you something very difficult. Just go in into Google, type Jacquard coefficient. Jacquard, I'll tell you how to calculate Gower coefficient. You'll actually get a paper. Gower would have written a paper and proposed this. So you'll get your hands on the original paper. You can actually read it. You'll enjoy reading it, I'm telling you, right? So start reading. You'll have to read a lot, as I said you. Machine learning, we need a lot of reading. So then there is something known as a Hamming distance, right? So they are all named after the guys who proposed them, right? So Jacquard, Hamming, so these guys had a lot of time and they did a lot of experimentation, right? Now, right? So I've given you some examples. These are enough. Okay. So Jacquard, Gower, Hamming, and there I've given you 4 5 examples. So choice of distance is very, very important. At least you should know between, you should be able to differentiate between a metric and a non-metric case. Categorical data, string data, never use the metric side of it. That's criminal, right? Use the non-metric side. That is very, very important. Okay. This was the point that I'm trying to deliver. Now, a basic fundamental question. Suppose there is some situation and I find none of the distance actually suits me. Let's say this is the kind of a thing. So can I go ahead and manufacture sort of my own distance? So the answer to that is yes, right? So distances can be manufactured. So if I say yes, distance can be manufactured, then there should be some conditions, isn't it? That how do you understand this is a valid legal distance or not, right? So what we'll do is we'll understand the three axioms. Axioms means the theories, right? So mathematics, we call them axioms. So we'll discuss three axioms. They are very, very simple. You'll know them. And the surprising thing is once you go through them, you'll say, okay, this is not a big deal. I already knew it, right? So we'll go through three axioms, which, so anything that you propose as a distance has to pass those three axioms. If it passes those three axioms, you can give your name, right? Example, Bhargavi's distance, and you can give it to the world and people can use it, right? So that's the idea. Okay, so any questions on this, just let me know. Otherwise, I'll open the slides, right? So the first thing is when the type of data in clustering analysis, that's why like the first slide says, it can be any kind of a data, interval scaled, binary, nominal, ordinal, and mixed type, right? I always said that the business thing, when you actually work in business, you'll see it's mixed data is the reality there. Now, when I'm working with mixed data, then you may say that which thing to use. And I think the question, whatever questions you have, the answers also lie in whatever we have been discussing. If you remember the first or the second session, I told you that the ratio data is the highest quality data, isn't it? And the nominal data is the lowest quality data. So if you have mixed data, then you're automatically this data will acquire the characteristics of the lowest quality, isn't it? Ideally, that should happen. In the world, it doesn't happen, right? When people actually mix a desi ghee with a dalda, they sell it for a desi ghee. That's wrong, isn't it? So proliferations generally should lead to the worst quality. So in machine learning, we don't do this. We always say that okay, whatever is the worst quality is whatever is the quality that I can safely assume, isn't it? So if it is mixed data, what I say is that technically this has the quality of a nominal thing only. So once I say that this data has lot of it will have nominal qualities, then I should pick up what kind of a let's say metric or what kind of a distance measure. Then I should pick up a non-metric distance measure only. R is very intelligent this way. We'll use the cluster package, and R uses the Gower method, right? So as soon as you give it mixed data, no need to choose anything. It's very intelligent. Automatically understand that you have to use the Gower thing, right? And Gower is I told you a non-metric thing, isn't it? So read Gower. So at least we have some homework, right? So for this weekend, let's read Gower and discuss it, right? So what is Gower's distance and how is it calculated? Okay. So that's the thing that I'm giving to you. The second thing is in why are we like the question that so there are two things that are still pending. One, I said that why are we discussing distances before clustering, isn't it? One idea you have, I gave you an idea because clustering means grouping similar objects together. So if I'm saying similar, then similar itself is a notion based on distances, isn't it? So there is a notion of distances there. So that's why we need it. So actually what happens, so I'm discussing the process of clustering also here. So the first thing that happens is, so this is the data that you will have, right? When we are doing clustering, then we'll have this data. This data has p columns and it has n rows. So p column and n rows, right? This is your data matrix. This is the data matrix that is supplied. Okay. Or you can say that this data has p attributes because we are talking of objects. Objects are clustered. What can be objects? People, place, anything else, right? So this p is the number of attributes that I have, and n is the number of cases, instances, whatever you call it. So the first step is it is converted into a distance matrix, right? Can you see this? It's converted into a distance matrix. The distance between a city to city is how much? If I say what is the distance between Bangalore to Bangalore, it is zero, isn't it? How different I am from myself if somebody asks me what is the distance between me and me, it has to be zero. Otherwise, I'll become a split personality, isn't it? Split personalities are personalities where the distance between me to me is positive, right? Otherwise, I'm not a split personality if the distance between me to me is zero, right? So this is one. So this has to be translated into a matrix, and the size of this matrix is n by n. N is what? Remember the number of instances. So it becomes a square matrix now. And what is the size of the square matrix? N by n. This is point number one. The diagonals are zero. This is point number two. And only you need to populate only one of the triangles. That's it, isn't it? Because the data in the upper triangle is also going to be similar. So why to populate it at all? And why this is important is, let's say you are dealing with the data which is 1 million rows or 1 million instances. So if I have 1 million instances, what would be my data matrix size? 1 million by 1 million. So that means in clustering, what happens is you generally, and this is the computing challenge. Remember this, right? So what is my computing challenge in data matrix? As I said, the I mean, if you look at the algorithm, it's very simple to understand. The P by N matrix is being transferred into a N by N matrix, right? because pairwise we are calculating distances. So definitely if you keep on calculating pairwise distances, this is the only form it will result into, n by n only, right? But 1 million by 1 million matrix may be a huge matrix, computationally intensive kind of a thing. And I know that this lower triangle and this upper triangle, they are similar, isn't it? I mean, so what I'm trying to say is that the distance between A to B should be equal to distance B to A, isn't it? So the distance between Delhi to Pune should be equal to the distance between Pune and Delhi. But surprisingly, I've seen some of the railway tickets where if you go from one side, the distance in kilometers, and when you come back from the other side, the distance in kilometers are different, right? At times that happens because probably the train or bus may be taking a different route, okay? But the aerial distances have to be equal, right? So so the step number one, remember this, what happens is the data matrix is converted into a dissimilarity matrix or a distance matrix. Distance matrix is also known as a dissimilarity matrix. So these two words are used interchangeably. Just remember it. In some of your packages will say distance matrix, some of your packages will say dissimilarity matrix. They mean the same, right? Just keep this in mind. Don't get confused. So this is the first step that happens, right? So that is why distances are important for us to know. Absolutely important. We need to know it. Otherwise, we'll not be able to take the first step. So this before you convert it into a distance matrix, there is one very important thing when we are dealing with, and this problem I discussed many times now. I'm just repeating whatever I discussed. Whenever you are dealing with intervalued variables, scale them, don't use them directly, so standardize them. So one of the methods of standardizing is convert it into a z-score. How do you convert it into a z-score? X is the value, x minus mu is the mean of the column divided by the standard deviation. So this is known as the z-score, right? So so sigma is the standard deviation of your column, x minus mu divided by sigma. So this is known as standardization, or you call it the z-score. Why do we do that? Very, very simple. I'll again give you the examples of the two variable that I always give you an example. So this is your age, and this is the income, right? So yeah, one more thing before I forget, right? Tomorrow we have a session in the morning again. So tomorrow, please, let's discuss the regression problem, whatever way you have been doing, right? So I to allocate a lot of time in discussing how have you tackled your regression problems, right? So I'll discuss that. So please keep that in mind. If you haven't worked, the night is all yours. Okay. So age is here. This is like, let's say 30, and this is 25, and this generally would be 2 digit, isn't it? And income would be, so this would be, I mean, if somebody has an income, then the age will lie between 18 to 70 maximum, or 75, right? That's all. But the income can be a very large number, isn't it? Talk of a 1 crore. 1 crore will mean 10 raised to the power 8 kind of a thing, right? 6 7 8 or 5 6 7, sorry. So this is, I'm talking of, let's say, a very big number, crore, like somebody crore earning crores, right? Then we have something like 25 lakhs, let's say. So now if you calculate the distance, what is going to happen from a measurement scale? We call this the measurement scale. So if you look at the measurement scale, this is 7 digits. If you look at the measurement scale here, this is 6 digit, and these are what, 2 digits. Remember that beta situation there I discussed, right? So measurement scales are very important, understand it. In regression, the betas depend on the kind of measurement scale that the independent variable has and the dependent variable has. So the beta is provides a matching between the two measurement scale. So here what will happen is, in the distance also, if you do not do anything, then what is going to happen is that this number is always going to dominate, and this number, this variable will have no say at all, right? Though this might be very, very important, isn't it? This might contain very important information, but will not have any kind of a say in this, right? To avoid this, we need to bring them to a apple to apple kind of a thing. So what do? We convert this, and I think I've discussed in other cases also, like I said, what that when you want to use your betas as standard weights, I advise what to do: standardize your dependent variable and your independent variable both. So then what will happen is the measurement scale will become equal, and your betas will actually represent the true weight. So what kind of weightage a variable is exerting on the entire solution. So here we are doing this, we are doing the standardization, and you know what happens if I standardize by the theory, you know that the values 99% of them will lie between -3 and +3, isn't it? And you know the reason why. Why is that? If you don't remember it, then just go back and ask Google this question: how much data lies between +3 standard deviation between -3 standard deviations and +3 standard deviation, right? And the answer would be 99 point something. Okay, so that's why I'm saying that your values will lie between -3 and 3 on both the sides, right? So now you're making an apple to apple kind of a thing. So the first step, intervalued data. So if you have mixed data, what do? The first step is standardize, right? So do a standardization of that. Of course, categorical data cannot be standardized, so we let them as they are, and then we go ahead with that. That's a step number one. And then what will happen? They'll all be converted into a distance thing. Okay. So scaling is the first thing. Always remember, it's very, very important in clustering to do that. Now I've discussed similarity would be 0 and 1. Dissimilarity is proximity is a combined name for similarity and dissimilarity, right? So there are many combinations. Some people call distance is also like similarity and dissimilarity. Whatever you believe, later on when you read, you may believe like what I say, or you may like evolve some other belief that you want. It all depends on you, but right now you can just think that these are four words that we have, right? So let's start discussing one of these distances. Okay, so the first distance that I'll start with is known as Minkowski distance, right? So Minkowski distance is written like this. So distance, and as I said, distance is between two objects. Distance between ith object will mean this will be a row, right? And this would be a row, I and j. When I say this would be a row in your data, isn't it? All of you agree with that, right? If you have any doubts on that, please let me know. And because you have and this is your coordinate system, right? Because we are talking of metric thing. Metric thing is applicable to ratio data, and a ratio data is known as ratio data, I told you in the beginning, because it has absolute zero. If it has absolute zero, it will have a coordinate system, right? Only coordinate systems have absolute zeros, right? So that means when we are using it on a ratio data, or when we are using metric distances, we are talking of a coordinate system, right? So this coordinate system, generally if there is a point, it is identified by the two coordinates, right? Isn't it? Let's say this is coordinate x1, right, and this is coordinate x2, right? So it will have some value. This point A will have some value, isn't it? So this will have some value on the x1 coordinate. Let's say x1 I will call it like this is ith data in the first coordinate, and it will have a value xj on the second coordinate, right? This is how I'm representing it on the second coordinate. Okay. So or you may represent it by some other way. Okay. Those are there. Now what is a, how do I write a Minkowski distance? Distance between I and j, two objects. These are two objects. When I say object, it means these are actually rows. When from a data set perspective, when I say object, I'm referring to a row, right? Because this is ith row, this is jth row, this is what I'm talking. Multiple columns, isn't it? So this will be, this can be written like this. Bracket, this is your absolute value, you know it. So on your ith coordinate minus the second. So let's say this is two column of data. What are we writing? Just so that you have a clear cut understanding. So let's say these are two columns, x and y, right? This is x and y, right? The two columns, and there are two objects. Let's say, and objects will mean nothing but your row number. So this is your row number I, right? Then there is another row which is row number j, right? And it will have some values. Let's say this has value 2, this has value 3, this has value 4, let's say here, and this has value 3 here. Just assuming. Okay, so if I want to calculate the Euclidean distance here, I think that's very, very simple. How do I calculate the Euclidean distance? I'll calculate is 2 minus 3, 2 minus 3 whole square plus 4 minus 3 whole square, right? Simple. This is how you calculate Euclidean distance if you have any doubt. So this is n, then I take a square root of this. So this is the Euclidean distance. And if I plot it and a coordinate this thing, then how do I do this? I think I've written it wrong, right? Just let me correct it. Let me write it on this. So this is the ith object. Let's say here it has coordinates what? 2 and 3. I've written it wrong. I'm sorry. I'll have to correct it. So this is, and then there is, this is the jth object. So this is the ith object here. This is the jth object here, and it has coordinates what? It has coordinate 4 and 3. I've written it wrong, right? I'll just like to correct it. So this is wrong, right? This is wrong. So how do I calculate the Euclidean distance? The Euclidean distance E would be equal to, I'll take the first object. This is the first object, the first one here and the first one here, right? So I'll take 2 minus 4 whole square, right? And then plus the second coordinate 3, and this is 3 here, 3 minus 3 whole square, which is effectively 0. This is square, and this value, if you look at it, will come out to be 2. So the distance between I and j is 2, right? Very simple. So this is the Euclidean distance. All of you know it. Now I've taken this example of only 2 attributes. Let's say there is one more attribute that we introduce, and this is the z dimension. This is the z attribute. Okay, this is z, and here they have different values. Let's say here it has a -1 value and it has a value of 2. Then what will happen? Just go ahead here, add this, right? So -1, -2, -1, -2, and then put a whole square here, right? This is how. So you keep on doing this, right? Generally you'll deal with n dimensions, so there would be n squares under this square root, right? That's the important point. What is the Minkowski distance? Similar to this only, it would be equal to, so I'll take the first object, right? So let's say the first object, the first dimension, minus the first object, the second object, sorry, the first dimension, and then I raise it to the power q, right? And there is a bigger bracket here, plus then I'll take the first object, right? And this would be the second dimension minus the second object, the second dimension, right? The second dimension. Let's say this is the x coordinate, this is the y coordinate, right? I can do, and then I can have the z coordinate, right? This is the this thing, right? So this thing, and then this entire thing raised to the power 1 by q, right? Now let's put this value of q equal to 1, right? Let's put q equal to 1 and let's see what happens. If I put the value of q equal to 1, then this is known as Manhattan distance or block distance or city block distance, whatever you call it. If I put q equal to 1 in the Minkowski, then this will become the Manhattan or the block distance. And how do I write it? Simple. This would be the mod x11 minus x21, right? x21, okay, mod plus x mod of x12 minus mod of x22, because these are mods, and one upon and 1 upon q means 1, so this would be added. So how does it translate? What does it mean? Let me look on a Cartesian thing. Or why is it given this kind of a name? Actually, when people go to Manhattan, why this is known as the block distances, and if you ask them where is the building, so they'll generally, because there is a symmetry, I think in India if you try it can be very risky. So probably how they answer it, that move 5 blocks to the right, then 3 blocks to the left, and you'll reach your destination. This is how they answer, 5 blocks to the right. So if I look at 2 points here, this is one point, this is the second point here. This point number 1, which has let's say the coordinates are 2 2 here, and the coordinates here are, let's say, assume 3 4. Okay, this is 3 4 here. So This is the aerial distance between them. This is the aerial distance, shortest distance. The other way of reaching this point could have been this also, no? I could have gone from here to here and here. So this is the Manhattan distance. So this path, the sum of this path is the Manhattan distance. Always remember, right? So this is how the Manhattan distance looks geometrically. So you travel all the components and then reach the point. That's known as the Manhattan distance. By looking at it, you can understand that the Manhattan distance will always be larger than the Euclidean distance. Now that also brings us to one more very important question. Will the clustering solution vary if I use a Euclidean distance? You have a choice of distances, isn't it? So will my clustering solution vary if I vary my distances, right? So if I use distance x versus distance y, distance measures, when I'm saying distance measure x versus distance measure y, will my clustering solution change, right? So that's one question. I'm not answering it right now, but at the end, but once when I finish clustering, this question should be answered. Okay, so we'll answer this question. So right, so have we understood what a Manhattan distance is? So Manhattan distance, and what is Euclidean distance? Euclidean distance is this, right? So in this, like, let's do one more thing. In this Minkowski distance, let me substitute q by 2. Okay, so if I do this, then what is going to happen is I have this. This would be again, let's say 2 minus 3. I'm taking numerical things here. 2 minus 3 because this is q, so it will become square. And I'm assuming only two dimension thing, right? Just to save time. That's all. 3 minus 4, let's say for example, 3 minus 4 whole square, right? And 1 upon q, 1 upon q will mean what? 1 by 2. And you know what is 1 by 2? 1 by 2, when you raise to power 1 by 2, this means we are taking a square root. So you can see that in Minkowski distance, if you take q equal to 1, then that will become a Manhattan distance. If you take the value of q equal to 2, it actually becomes a Euclidean distance. So it's a generalized distance, right? It's a generalized kind of a distance. The last we discussed GLM, isn't it? Generalized linear modeling. So if you take family equal to binomial, it will start fitting a logistic curve, right? If you take family equal to Poisson, it will start fitting a Poisson curve into it, right? So it's a generalized kind of a thing. It can take whole lot of values depending on the variations that are done. Okay, so this is what is there. So we know two distances now, and you can take L equal to infinite also. So if Q is very very large, then it translates into another distance. You can call it the L infinite distance or infinite norm. This is also known as the infinite norm, right? So it will if the q value, if you take as very very large, then this is known as L infinite or infinite norm, NORM, right? Norm is a word that comes from matrix algebra, so it is known as infinite norm, right? This is infinite norm. Okay, now, so q equal to 2 we have seen. Generally, you will not require to decide anything on this, right? This distance has actually come from the classical statistics, let me say. Like when those guys read it, they have this distance and then they discuss like what happens if I vary q, this and that, right? When you are into a machine learning thing, you don't have many choices. So either you will use q equal to 1 or you will use q equal to 2 maximum. If you say if I'll use q equal to 3, that exists. I'm not saying it doesn't exist, because if the value q equal to infinite exists, 1 exists, 2 exists, infinite exists, then definitely 3, 4, 5, 6 should also exist, isn't it? So by the law of induction, isn't it? By the law of induction says if the value of 1 exists, 2 exists, infinite exists, then 3, 4, 5, 6 will also exist. I mean, they have to exist. So what I'm trying to say is what a q equal to 3 means in machine learning, or is there any practical utility of that? My answer would be no, right? So Minkowski distance, for mentioning that it is a generalized distance, probably the utility stops here. Practically, it is either you will use the Manhattan distance or you use the Euclidean distance. That's all, right? Nothing more than that. But the only thing is that you when you are using Euclidean and let's say Manhattan, then you can just remember they are not like two different distances. They are the same family, and that is the Minkowski family. That's all, right? That's just the thing, just to keep in your mind right now. Otherwise, in detail, there is a whole lot of stuff that is there, that if you change this, then this happens, that happens, all is there. But I'll not advise in the beginning go for this. Don't do that, because clustering is your aim, not like let's say the distance thing absolutely is not your target right now, right? So this is how I'll say. Okay. So when we talk of distances, I think I said that there are three axioms of distances. And because these are axioms, so if I propose something, why do we have axioms in mathematics is that if you, as a mathematician, if you want to propose something, and people keep on proposing daily, some or the other theorem keeps on coming, and that is proposed like an axiom that these are the rules that it follows, and hence in the end you say it is a theorem, it is a valid theorem, right? So this distance also has axioms, and someday if you want to come out with your own measure, then and if whatever measure you are proposing, if that happens to follow these axioms, then that would be a distance. Go through this paper. I'll pass this paper, Abidi's paper, right? Harvey Abidi's paper. If you go through it, he has actually proposed a kind of a distance. He has picked up this and actually proposed a kind of a distance, and he has proved that it meets the three axioms, and hence it is a valid legal distance measure. Okay, so the first axiom is distance between I and j should be greater than or equal to 0. Because I believe in this axiom, so distance measures can never be negative. There cannot be a negative distance. This is point number one. So if you scale it also, the value should lie between 0 and 1 and not between -1 and +1. And that is the reason similarities will always be between 0 and 1 and not between -1 and 1. Okay. These two can be read as common axioms because you said that I told you three axioms, but here you see four, isn't it? But these two are one only. The distance between I and I, and this is what I said, the distance between me to me should be 0, otherwise it's a split personality, right? So distance between Hyderabad and Hyderabad should be 0, until unless we are talking of a Hyderabad which is in Pakistan also, right? So between them definitely there would be a couple of thousand kilometers of distance, right? So and this, because of this axiom, all the values are positive. What is the bearing of this axiom? All now, let's start looking at the distance matrix. I told you what is the properties of the distance matrix. The distance matrix is a n by n matrix. This is what I told you, right? And the diagonals are 0, isn't it? We discussed that the diagonals are what? 0. The zeros are not symmetrical, but I mean the same zeros, right? So this, because of this property, the diagonal, this property is a bearing on the diagonals. My diagonals become 0 because of this property. Then distance between I and j should be equal to the distance between j and I. When I believe in this property, then what is going to happen? The lower matrix and the upper matrix have to be identical, right? They have to be identical because of this property only, because of this axiom only. So if they are equal, then to save space, I can just take this much. I may not even worry about the diagonal also, because if it is 1 million instances, rows or objects, then at least if I know that the diagonals are 0, then I save a space of 1 million again. And the third one is also known as the rule of the triangle, right? So if you look at a triangle, what does it mean? So you can look at it like this. Let's say this is the vertex I, this is the vertex j, right? And this is the vertex k, right? Ijk, this is the vertex. So distance between I and j, this distance between I and j has to be either greater than, or sorry, has to be less than or equal to the distance between ik and jk, right? And in a distance, you know the property, the triangle property, isn't it? What does the triangle property say? That the sum of two sides have to be greater than or equal to the third side. That's the property of closure. If this property doesn't happen, you can't close a triangle. You will not get a triangle, right? You will get something which is open, which will have three sides but is open, right? So something like a Bay of Bengal. So if you want to close a triangle, this is also known as the property of closure. So the sum of two sides have to be greater than the third side. That's very, very important. Or in common life, in common, let's say, distance kind of application, you can always say that the direct distance, because when we are dealing with distance and when you are referring to Euclidean distances typically, that the direct distance between 2 points is going to be different than the via kind of a distance. So if you travel from some if you want to travel from Delhi to Hyderabad versus if you travel from Delhi to Mumbai and then to Hyderabad, definitely this distance, because this is a via distance via Mumbai, it has to be greater than the direct distance between Delhi and Hyderabad. Now, does it apply for all metric distances? Yes, I told you these are axioms. All the distance, metric or non-metric, have to follow these three axioms. Otherwise, they are not distances simply. So the question of whether Euclidean follows it, whether Manhattan follows it, or does the L infinite norm will follow it, or if I use some other Jacquard follows it, or does Gower follow it, they have to follow it. Hamming has to follow it. I mean, there's no other. Maranovic has to follow it, right? So that is what, because these are three axioms. Anything is a distance only and only if it follows all this stuff, right? All these three. So remember that, and this has a bearing on my metrics also, right? Because there is an axiom. That's why I use this and I slice and dice my this metrics and make it bit, let's say, computationally bit easy, right? That's all. So that is there. Okay, now what else about distances? So we know how to calculate distance, isn't it? We are not getting. So this is Euclidean distance. You know it very easy. You can do some examples. So this is some example. So you can see here. This is the data. So just what I want, you know how to calculate a Euclidean distance. That is what, not the focus here. What I want to focus here is, this is my data matrix, isn't it? What is the size of the data matrix here? Do you see this? This is how many rows, or probably you can write it, because rows are always written in the first. So 4 into 2 matrix. So this 4 into 2 matrix, when you convert it into a distance thing, how much should it be converted to? It should be converted into a 4 by 4 matrix, isn't it? 4 by 4 matrix. Diagonal should be 0. You can see this, all the diagonals are 0. This is a 4 by 4 here. These are 4 here, and all the objects are written. What are the name of the what is the headers and row things? They are all name of these objects. So this is 4 by 4, you can see it, and this is equal to this, you can see this, right? And this is equal to the upper triangle and the lower triangles are mirror images, right? Exactly a mirror image. So a diagonal is like a mirror, so a lower, and this is like a mirror image. Okay, so and how does this happen? P1, we'll calculate the distance between P1 and P1 has to be 0. The distance between P1 and P2, distance between P1 and P3. So all binary distances are calculated and put here, and you'll see that it will always be converted into a n by n matrix only. That's the only way, right? That will only result, right? So we know it how it is done. Good. Now let's see what else. So this we know it now, right? So this is a representation form, right? Sigma k equal to 1 to n, sigma pk minus qk r raised to the power 1. So I had written plus plus to show you. Now if I don't want to write this plus plus, then so whenever we write, there can be expanded form and there can be a summarized form. So this is the summarized form. So sigma is when you don't want to write plus 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 plus, then you can just say sigma k equal to 1 to n. That's the summarized form, summarized representation, right? We all know it. So this is city black. This is also known as supermum, right? Yes, one more name, supermum. L infinite norm distance, right? We'll never use this R infinite. Don't worry about it. So we just know it exists. That's all. So Minkowski, if you look at it, generally those values will be higher than the thing. Now, let me come to the Mahalanobis distance. What is the Mahalanobis distance? So, one way of writing your Euclidean distance in matrix algebra. In matrix algebra, when we write a Euclidean distance, let's say we have a vector P and there is a vector Q. So, one way of writing, so in a coordinate geometry form, you know it. How do we write it? This square plus the difference of the two n square. So this is what method? This is the coordinate geometry method, right? Then we can have the vector algebra method also, or the matrix algebra method. In matrix algebra method, if I have to write the same thing, I'll write it like this. P, let's say this is a P vector, two dimension vector only, P minus Q, right? multiplied by P minus Q transpose, right? P minus Q transpose, P minus Q transpose, right? So this is nothing but my Euclidean distance representation. And if I want to expand it, what will it result into? This thing. If I expand it, this is what it is going to result. Okay. So this is my matrix algebra representation. Now, what is the Mahalanobis distance? Mahalanobis distance is a inverse weighted Euclidean distance. Point number one. So it is the basic stuff is Euclidean distance only. But what Mahalanobis saw is that if you have outliers, right? Do you see this like example, this A and B? If you look at this, then this will be a very big distance, isn't it? Use distance out there. And think of two situations. There are only two dots here, right? Two, three dots here. And there is a whole bunch of dots here. But if I use Euclidean, then what will happen? The A and B will happen to be, now think of these two situations. Now think of this. Just think about it. Everything here in machine learning is very logical. You have to just think. That's what I'm saying. Nothing very difficult. It's only that people don't want to think. That's the problem. And then there is mathematics involved. There is no mathematics. Think of these two situations. There is a point A out here, right? There are a bunch of small points here. There are small points, right? 4 points, let's say, to be precise. And there is a B point here. This is situation one, right? I'm giving you situation number one. Now I go to situation number two, right? I go to situation number two. Okay. Now, same, the A and B are similar. They have similar coordinates, right? If they are not seeming to be similar, assume they have similar coordinates. Let's say the coordinates of A here are 2 2. Just assuming this is they are 2 2, right? And let me assume the coordinates here are 100 and let's say 3. Okay, 100 and 3. This is the coordinate here. The similar coordinates of the coordinates of A and B are similar in this situation also, but there is a difference here, right? What do I do? The number of points that I have is like it's densely populated this time. So instead of 4 points, let's say I have 100 points in between this time, right? You can see I'm populating it. There's a density out here. Okay, it's a dense area now. The area between A and B is bit dense. Okay, that's what I'm saying. Now, let's say I use Euclidean. I want to find out distance between A and B. Okay. In situation number one and in situation number two, do you think there is going to be any difference? Practically, there is going to be no difference. Why? Because the coordinates haven't changed and the formula for calculating Euclidean is constant. So it has to be 2 minus 100 raised to the power square plus 2 minus 3 raised to the power square, isn't it? What it doesn't take into account is the density in between. Now, why is that important? In this case, B is definitely an outlier because there is no density throughout the entire distance. That is why this is an outlier lying away. But in this case, is this really an outlier? I'll say no, because the space between A and B is densely populated in this case, right? That's why this is not a case. B is not an outlier. So we need a mechanism where the distance between A and B in that case would be a very large distance as compared to the other distances. In this case, the system is not able to differentiate between the two situations. Here it's actually an outlier, here it is not an outlier. So what Mahalanobis did is that he introduced the concept of reverse weighting. Now what is that reverse weighting that he introduced? The reverse weight is the covariance matrix. So generally we represent the covariance matrix by a sigma. Don't assume this sigma to be a summation. This is not plus plus kind. This is not a summarized form of a plus plus. Just a representation of the covariance matrix. Covariance, all of you know that we can calculate. Covariance is again what? It's a bi kind of a thing. That means you calculate it between two bivariate kind of a measure, isn't it? So you calculate covariance between two variables always, right? That always happens, isn't it? So we always calculate it between two variables. That is how we do it. Okay. Um, In case like you need a break, just let me know. Otherwise, I think we have lost some time in the beginning, so that's why like I'll not take a break. I'll continue. But in case you need it, just let me know, and then we can stop. I think because we lost some time, so we need to cover that. So this sigma is my covariance matrix. So what he did is he did a inverse weighting of this, right? So if this thing is densely populated, what will happen is the covariance would be high, right? The covariance would be low, sorry, because there is a gradual change here. Covariance would be low. But if you see here, when the data changes abruptly, then the covariance metric will have higher values. So this inverse weighting, what it does is that it will not make drastic changes in the values, right? This is how it is able to, let's say, deal with outliers and all those things. Malnobe resistance, you'll never have to calculate manually. There is a package available in R. You can search it, and you can just put a data set, make your own data set which has a lot of, let's say, outliers, something, and compare the Malnobish distance and the Euclidean distance. Example, you can see here the Euclidean distance says the distance is 14.7, whereas the Malnobish distance says it's only 6 because it is not an outlier. And if you reduce the number of points here, then the Malnobish distance will start tending towards the Euclidean distance, right? So that's what happens. So it's not prone to outliers. That is one thing. It knows what is an outlier and what is not an outlier, right? That's the advantage. That is why Malnobish distance is also used to decide outliers.
Amit,
So typically, if you have like done that standardization, there will not be a question of outlier because the values will lie between +3 and -3, right? So then the question of outlier doesn't come. But in some cases, what happens is the this process of standardization, we don't use it because see, whatever number of standard, see, understand one thing, standardization is also a transformation, isn't it? If we are transforming data from one form to the other form, the when we do standardization, they solve one problem, there is no doubt about it, but they give rise to another problem. In machine learning, we always say there is nothing free, that there is absolutely nothing which is, there is no free lunch. Transformations solve the problem of outliers that is there, but tying back the result to the original thing at times becomes very, very tricky. So in some cases where the measure differences are not very drastic, what we do is we may not transform the data, right? And we may say that, okay, I'll go ahead with the original data and calculate distances. So this is meant for that kind of a case. But you are right. If you transform a data, then looking for outliers is a futile exercise. Then you should not worry about even using Malanovis distance, right? So that is why when initially when you are doing a lot of clustering, and that's why I said that always do a kind of standardize your data, turn it into a z-score. If you turn it into a z-score, Euclidean is more than enough for you, right? Or a Euclidean or a Malanovis are good enough, right? Need not look at the Malanovis. That's right. Okay. Coming to similarities or the non-metric thing, right? So the non-metric distances. Generally, as I said, that we don't denote it by D, you may denote it by S, right? It's just a matter of representation. So S between P and Q equal to 1 for maximum similarity, or P equal to Q, right? But if P equal to Q, then that's the maximum similarity, right? Either they are actually similar or it's the same thing, P equal to Q equal to 1, right? And as I said, all the three axioms have to be meet, and SP by Q equal to 0 if there is minimum similarity. So the first axiom is met. SPQ should be equal to XQP, right? So this is the symmetry property, and the other, all the things will be applicable here. All the three axioms would be applicable. Now let's look at a situation where we are calculating similarities, or you may call it a non-metric distance between uh, a binary kind of a situation. Binary kind of a situation, as I said, could be a computer level, machine level code, right? 1010 kind of a thing. So let's say there are two string. What is discussed here is, let's say there are two strings which are here. There is one string S1 here and there is another string S2 which is here. So there are two strings which are here, right? And these strings consist of a binary situation, let's say 1010. Also, there is one more before I forget, let me also give you some more homework, right? So all of you need to read and these two distance you have to read and discuss, right? Absolute must. There is something known as edit distance also. That's very, very important because the edit distance is one of the most important distances when you get into the area of natural language programming, NLP. When you get into NLP, and NLP is a very important thing, right? With people talking of artificial intelligence, NLP is one of the pillars of artificial intelligence. So NLP is based on something known as a edit distance, or this is one. So please make a note of it. All of this you have to read. I'm not going. My contribution was giving you these names, right? That's all. And this is, and my contribution stops here. So if you ask me what am I going to do next with this, nothing. Levenstein distance. How do you pronounce? I don't know. Levenstein, I think this is how you Levenstein. So see that it's all available. All these things are available in our ready-made packages. So please, these things in third cover, right? These three distances you have to read, discuss, and come back, right? You have to tell me what does it mean with a small example if possible, right? And make a slide also so that I can use it in the next batch. When the next batch comes up, I'll use that. Of course, I'll give you credit. I'll put your name there, right? So edit distance, Levenstein distance, and the Gower distance. These three distances to be read by you and understood. Okay. So let's say this is the kind of a thing that we have, 1010 kind of a thing. Then there is one more string, 1100 0011. This is the kind of things which are available. Okay, so these are two strings. Now how do we understand that these two strings, now this can be this is a binary kind of a case. When I was discussing about the DNA thing, then we had those four characters, ACGT kind of things are repeated. Those four characters are repeated in the gene sequence, right? They are billions in numbers, as I said. So let's say M01 is, now you will compare the basic idea. You will compare it position wise. First position, I have a one here, I have a one here. Oh, I got a match. A one is matching with one. Second position, I have the second position, I have a zero here, I have a one here. So this is a M01 kind of a thing. First position I have a zero, the second position I have one. This is a 1-1 kind of a situation. The third position I have a one here and I have a zero here. So this is a 1-0 position. I can have four combination only. First I have one, here I have one. First I have a zero, I have a one here. Second, I have one here. I have a one. I have a zero here. Sorry. First, I have a zero. There are only four possible combinations, right? When I'm looking at the string. So let's say when and I'm doing accounting, which situation I'm encountering. So one of this situation will only come. So I can make a matrix kind of a thing out of it. So M0 is the number of attributes where P is the name of the first string. You can call this P and this as Q, right? So this is P, this is Q. So P was 0 and Q was 1, right? So M01 numbers. M10 is the number of attributes where P was 1 and Q was 0, right? These are all attributes, isn't it? One attribute, two attribute. You can call it featureization. It consists of, and let's say the string length is 100. Let me assume it. So how many features has this strings have? 100 features, right? You can imagine it to be like this 100 variable kind of a thing, like this. So this is, they are that's why they are known as features also. This is from an old book. That's why they keep on calling it attributes. You can start calling it features. So the number of attributes, P was 0 and Q was 1. Then attributes where P was 1 and Q was 0, right? So we have these numbers. Now there are like SMC, simple matching. Simple matching coefficient is also one of the distance measure. This is how you calculate it. M11, probably let me make it easy for you to see. So you can see here that this is M11, M00 divided by everything. Of course, you can see the denominator is the total. So what is going to happen is the numerator is always going to be smaller than the denominator. So we'll always get a number, and these are counts. This is a count data, isn't it? Count data is always positive. So it will be less than one and it will always be positive. We know it, right? When you're calculating the Jaccard coefficient, then there is a difference. Do you see here? We only consider the N11 thing, right? Just the M11 thing, and the zeros are neglected. And so this is the difference between Jaccard and the simple matching coefficients, right? So this is a simple example which is about a binary thing, and similar thing can be applied to anything, I mean, right? So okay, now coming to, and cosine similarity also, if you look at cosine distance also, then that is also a similarity thing. Cosine similarity means your the correlation is also known as cosine similarity. So one, you had done those calculation, x1 minus mu1 divided by sigma 1 and multiplied them. That was one method of calculating. If you want to calculate correlation using vector algebra method, then this is simple. D1, this is the dot product, right? Not the cross product. Dot product, this is the dot product, will not have any, this will not result into, this is also known as a scalar product, because the resulting quantity will not have any direction, right? Divided by, this is the modulus of D1, this is the modulus of D2, which essentially mean the distance of the vectors, right? So you can see that this is how it is calculated, and this is nothing but the correlation. This is actually the correlation. If you calculate a correlation between this data, you'll get the same thing here, right? And how do you calculate the distance? Distance equal to, because this is similarity and distance is actually a dissimilarity. So what will you do? You have to put it 1 minus, right? All these things are available. Don't worry about it. Nothing this thing, right? So now what have we done? We have finished this idea of distances, which is useful. Just remember very quickly, it can be two types: metric, non-metric. Metric means the ratio data, non-metric string, character, nominal, any kind of a data. If you want to match two strings, you will have to get into non-metric. Non-metric, I told you, Gower is by default that R is going to use. That is why please read it. NLP, there are two distances which are very important. Levenstein, I told you, and the edit distance. Levenstein is a very popular distance metrics in the world of natural language programming. So please read it. So there are three things that you have to read, come back and tell me that okay, we have read it and understood, or half understood, whatever. So now we are ready to go and understand clustering, right? So let's go and understand what is clustering. So what is cluster analysis, right? So cluster means a collection of data objects, right? In telecom also you say it's a cluster. We are dealing with a cluster. Cluster means a group, right? So cluster of switches, cluster of something, whatever. So cluster is a collection of data objects, and clustering, right? That's a verb. That means we are doing something, we are grouping. So when we try to group similar objects, then we are doing clustering. So clustering is a unsupervised classification. That means there is no predefined tool, right? There is no predefined class. You don't have any predefined thing to tell the system, and you give that data to it. You say, I don't have any examples to tell you, but I know there are groups in this. At times I'll tell the system these many groups. At times I'll say, okay, I don't know the number of groups also. Why don't you help me? Right? So remember this. At times I'll know how many groups. And at other times I may not know the number of groups, right? So there can be two situations there. When do I know the groups? Of course, when am I an expert, right? If I'm working in a telecom company on the marketing side, and I'm understanding my customers, then I know the number of types of customers that I have in my data. So clustering fits very well, is one of the very important tools of marketing analytics, right? So if you get into this area of marketing analytics, or if you get into a company which is into providing services in terms of analytics, then you will keep on getting business data. So you might get financial analytics, you might get marketing analytics. So cluster is a very important thing from a marketing analytics perspective also. Why is it important? Is so that you can know, if you look at the process of something like in marketing, when you do marketing management, a MBA in marketing management, then you are taught something known as a strategic marketing process. That strategic marketing process consists of three parts: STP, right? And all companies have to do it. S stands for segmentation. So segmentation translates in a from a machine learning perspective, it translates into clustering. So segmentation is nothing but clustering. So the marketing guys have know a lot of fundas here and there, but they'll have to come to the machine learning guys to actually get it clustered and segmented. So T stands for targeting and P stands for positioning, right? We are, because we are not into a marketing class, so we are not discussing these two things, okay? But just to understand that why is it important from marketing analytics is important, because every company has to do strategic marketing, and there are three steps into strategic marketing: segmenting, targeting, and positioning. So segmenting translates into clustering, right? So if like I am a seasoned marketer, then what will happen is, if I worked into let's say telecom, and telecom uses this very very heavily, one of the maximum user. So if you have worked in telecom for let's say 15 years, then what is going to happen? You'll know that these are the types of customer that I have, or these are the number of groups that my customers can be divided into, right? So you know it because of your experience. That's why I said at times you know, at times you don't know. If you are a newbie, you have joined a telecom company for the first time, then you'll not know how many natural, let's say, groups of customer there are. So you'll have to then tell the system, I don't know, please help me on that, right? Now, so we move on, right? So clustering we have understood, right? It's a unsupervised learning. That's very, very important. So we are clustering. Why we are discussing clustering now is because we have discussed all supervised learning cases. Your regression is a supervised learning. So we did supervised learning. Now so I thought, let me break from that, and they were all statistical modeling. So there are two things when we are doing clustering or cluster analysis. One, it's not a statistical model, point number one. It is unsupervised, right? So that's why like clustering analysis is important. So what does it mean? This is what it means. These are three groups: the red ones, the blue ones, and the brown ones. So what do we want to do? So clustering does two opposite things if you look at it. It should pack similar kind of things together and separate, packing and separating both at the same time, isn't it? You're flocking together and you are moving at a distance also, right? So intra-cluster distances should be minimized and inter-cluster distance are to be maximized. So minimization and maximization, two objectives at the same time, right? Isn't it? There are two objectives that are to be obtained at the same time. Two objectives. So this is a two objective problem. Minimization also and maximization both at the same time. Now, are they dependent on each other? Yes. If your minimization thing changes, then the maximization thing will also change. They are dependent on each other, right? So somewhere we have to have a trade-off kind of a thing. Okay. So look at this now. The second point. So we have understood now the clustering. As I said, in machine learning, there are easy algorithms, there are difficult algorithms. So clustering is assumed to be supposed to be a easy algorithm, but believe me, it is very difficult to use. Why? Let's look at this. Let's understand this. That what am I trying to say? Look at this situation. Just look at this diagram and tell me how many clusters are there. Some of you will say two clusters, right? Are there two clusters? Yes, you will say, see, yes, this is one cluster and this is one more cluster. Very clearly, we are seeing a gap. Some of you will say, no, there are six clusters. Some of you may say six clusters also, isn't it? There is a clear cut gap, right? This is six clusters out here. So, very clearly, from my naked eye, I can see 2 to 6 cluster solution, isn't it? So, the notion of clustering is at times ambiguous. Remember that. This is point number one. So that means it brings us to one more problem. If there are two people who propose a solution, a clustering solution, their clustering solutions may be different. Somebody may say two, somebody may say four, somebody may six. Deciding whose solution is correct, there are no hard measures for that because this is not a statistical method. Had this been a statistical method, you cannot have two betas, right? There is a clear cut process to do that. there will only be one beta at the end of a regression exercise. You do it in whatever system you like, right? But here you use the same system. Just because two people do it, there may be a varying solution to it, right? So the notion of cluster can be ambiguous. That's why this statement. And that's the biggest challenge. So the biggest challenge in clustering, easy to run kind of a thing, but what is the number of clusters, which is the right solution? That's the central problem of any clustering solution that you're providing. The central problem is always what? And I'm assuming that you have used the distances properly, right? If you mess up with your distances, then any solution is a wrong solution, right? Isn't it, by the way? So if you use prime numbers and then do something like that, then that's anyway a wrong solution. But I'm assuming that you have used the distances properly. You have standardized where you need to standardize because you are starting. If you haven't standardized, then you have, if there are outliers, you were prudent enough to identify that their melanobis should be used and all those things. So all those steps you have taken correctly. Even after that, it can be ambiguous, right? That's the difficulty. So what I'm trying to say is, because I followed the right procedure at every stage will not automatically lead me to the correct cluster solution, right? This is what I'm trying to tell you. It's not dependent on the quality of the process per se. At times it it's just ambiguous, isn't it? It's just ambiguous, and you have to find it out. The system will not tell you that you actually had ambiguous solution and you have been in a hurry and you have recommended two, which is wrong. Just understand it because I'm showing you it in two dimension. You are able to see it very nicely, and we are talking all this. But let's say these are 15 dimensions. How can I show you 15 dimensions? Can we see these natural boundaries? We cannot see it. So understand it this way. One, visually nothing is available. I know there is some dark situation out there, and this can lead to ambiguous thing. This is where your expertise in clustering comes. And this is what people fail to notice, that this is what is actually required, right? So this is the problem also that we are bringing in, though this is a simple thing, but there is a challenge attached to it. Okay, fine. So somebody can say two clusters, somebody can say six clusters, somebody can say four clusters also, right? So everybody is right. I mean, visually everybody is right. You can't challenge this. So there should be some other method of challenging it, isn't it? So this is what we look at. Can we arrive to a good clustering solution? Can we remove this uh, haziness around this, right? So now this is fine. So now we come to the types of clustering. So clustering can be two types, right? And it's all attached to the idea. Do I know my final cluster solution? Do I have an idea of how many clusters I want, or do I have no idea of how many clusters are there in the solution, and I want the system to help me on the number of clusters, right? So clustering can be two types. Uh, One is known as the hierarchical, and the second one is known as the partitional. Some people call it k-means also, whatever you prefer to call it. Popularly, this is known as k-means, right? What does k-means means? K is n is the number that you have to supply. When you use k-means, right, it means that you are familiar with the cluster solution. When I say cluster solution, it means the number of clusters. So you are familiar with the k with the solution, and that k is your knowledge. Okay, given this data, please partition it into 5 groups. That's why this is known as a partitional method or a k-means method. An analogous method is k-medioids also, right? K-means means the parameter that I use. I'm using means, and medioid means I'm using the medians, right? So we'll discuss this as we go along. But just right now, I'm just telling you there can be two types of clustering: hierarchical. There can be hierarchical methods or there can be partitional methods. Partitional methods can are known as k-means or k-medioids. Means and medioids are different, right? K means you are the supplier. Partitional method means you are the supplier. You have to tell to the system how many groups you want. Hierarchical clustering is generally, why do we call it hierarchical? Hierarchical because it is something which can be organized like a tree, isn't it? Hierarchy, we say there is a hierarchy. In your organization you have a hierarchy, isn't it? Organizational hierarchy. So how does it start? At the bottom you have a whole bunch of people, then there would be a smaller bunch of people who are known as managers, and then up above them there would be still a very elite kind of a group who are known as executives. And these executives then this is like a pyramid thing. The pyramid will have an apex, and that is your CEO or the owner, right? Or CEO, whoever he is, right? So this, the pyramidal structure is also known as a hierarchical structure, right? So also hierarchical things roll up, isn't it? So you roll up into somebody into your organization when you say that I report into somebody. So somebody is your boss, and you will have subordinates also. So rolling up, rolling down, right? So that's the hierarchical thing. So here also we get some similar kind of a structure here. That's why this is known as a hierarchical thing. When we are talking of hierarchical, just remember hierarchical can be two types. One is known as agglomerative, right? Agglomeration. You know agglomeration means what? Combining, agglomerative. And the last one is known as divisive. Divisive means dividing, right? The way like Rahul Gandhi did divide people in caste in Gujarat and try your luck. So divisive thing, agglomerative and divisive, right? So this is what. So what are we going to do? The first thing is, what are our objectives now for the remaining portion? We are going to understand the first objective is that this hierarchical thing. What does a agglomerative mean? What does a divisive mean? That's one. uh, Partitional, I've already told you, it's dividing into that. That's one. Then the second thing is we studied something known as distances, right? So one portion we have understood that this is about that the data is converted into a distance matrix that we have done. But one more issue I told you, your data, that your clusters are groups. So how do we and remember this slide, refer to this slide number 21, probably let me take you there. This slide number 21. Here we are saying intra-cluster distances. Now, what distances are we talking of? What do we minimize here? And how do we find this distance between two groups? How do we find that? Which distance are we talking of, right? So that's one more thing that we'll define, right? So, okay. So hierarchical clustering. So partition clustering is very, very simple. It's about, you say that these are my, this is my data, and you say make two portions out of it, make two clusters out of it, right? So if you say two clusters, so then what happens is that you make two clusters out of it, right? Because you are the supplier. Okay. So just a minute, I mean my son has come, he's just saying I'm going to sleep. Okay, yeah, sorry. So there are like two, there is this data, and then you are making two two parts out of it, right? And you are telling the system, please make two parts out of it, right? So this is known as partitional clustering, or clustering, partitional clustering. And this is what a hierarchical thing is. Look at this. This diagram, this hierarchical thing, this tree kind of a structure is known as a dendrogram, right? Dendro, there is a R there. Remember that. Okay. So there is a dendrogram out there. It's DNDRO, dendrogram. So sorry. So if you look at this dendrogram, how does this result? So what happens is these, let's say these are 4 points, right? P1, P2, P3, P4. So what will happen is these are known as stages. At the first stage, in the distance matrix, if you look at the distance matrix, this is the distance matrix, right? And you saw that how had we made it, P1 to P4. This is how we had made it. And here we had, again we had P1 to P4, right? P1 to P1 is always 0, P2 to P2 is 0. Now in this distance matrix, if you go back in the earlier slides, you'll find P2 and P3 is the least distance. You're finding similar things, isn't it? So P2, P3 is the least distance. So you'll find the least entry in the cell where P2 here and P3 from here. So this cell will have the least entry, right? Because this cell has the least entry, so this will combine in the first stage. So these 2 points will combine and they'll become one cluster, right? So this, you can see it from this cut set. This is also known as a cut diagram, right? If you are familiar with this area of graph algebra, or graph theory, this is one subject in mathematics. So graph theory, if you look at it, things are represented that way. This is known as a cut diagram there, right? In graph theory, known as a cut diagram. Okay, so P2 and P3 in the first stage, they combine and they become a cluster, which we are representing by this elliptical kind of object. So P2, P3, you can see this is the elliptical object. Now P2, P3, so what will happen to this distance matrix? The distance matrix would be reduced by 1. So after the first stage, if 2 points combine, then you'll have a distance matrix which will be of the order of n minus 1 into n minus 1. Remember this, right? Why? Because 2 points have now combined and that has become one cluster, isn't it? And this cluster has to be represented as a single entity only, or you represent it by C1. So P2, P3 will vanish and C1 will appear there. So P1, C1 and P4 would be there. P2 and P3 will lose their existence because they are merged and become a cluster. In the second stage, this C1 entity merges with P4. You can look at this one. This C1 merges with P4. Okay. So this happens at the second stage. At the third stage, what is going to happen? So let's say this now becomes C2. C2 is the bigger one, right? Now this C2 merges with P1, and what do we have? We have this one whole monolithic thing, right? One blob, you can call it. So a single blob we have, right? So this is C3, a monolithic bigger thing. So when you go for hierarchical clustering, I told you there can be two kinds of thoughts. One is known as agglomerative. I'll come to that, what is agglomerative and what is a divisive thing, right? And the second can be divisive. So the agglomerative philosophy says that if you have n objects, then they are n different clusters, isn't it? So why are you in a hurry to probably merge them? Don't merge anything. They are actually n unique clusters. This is what the philosophy says. Then you say, no, that's fine. We understand, right? And also understand in clustering again, like this, there is one more thing, isn't it? It would it not be a good idea if you see that all of us are allowed to have a country which is like our home, right? So I am my home, I am my family. So and that is a country. So I am owner of a country. Then my father can become a president there, and my mother can become a prime minister. I can become something, right? So this is the entire country, and I can decide things. Wouldn't it be good? I can have my own rules, and my neighbor is another country. I can decide how to tackle those. Versus I combine everything and say the whole world is actually one big country, right? So agglomerative means that we say individual identities are respected. They are different kind of, they are unique clusters. Then we say no, combine them. So they'll start combining and ultimately reach one cluster. So agglomerative cluster gives me a clustering solution which lies from n cluster to one cluster. It starts with the assumption that all clusters are unique, combines them, and puts them as one cluster. Divisive is the opposite of it. Divisive says that everything is one cluster only, right? It's one only. So they say they believe into the philosophy of the world is one, right? So they say the world is one, and then you insist. So they start breaking it down, and they provide you a solution which is one cluster to n cluster, right? So divisive is 1 to n. Now looking at a dendrogram, can you understand whether this is agglomerative or divisive? No, right? No, the dendrogram is similar, isn't it? Theoretically only these are two different things. So you say this is n to 1 kind of a thing. Now the important part is the truth. These are two extremes. When you say the world is one and when you say that every family should become a country, these are two very, let's say, extreme assumptions. The world cannot work with both of them. The truth lies somewhere in between. That's why we have notions of countries, right? So we are a country like India, isn't it? So the truth lies somewhere there. So that means in clustering also the solution, the actual solution, practical solution will lie somewhere between n and 1. Here also 1 and n, right? So that doesn't matter. You use agglomerative or divisive, hardly it matters, right? So theory, there is a difference. But if you ask me practically, if I use agglomerative and divisive, will it give me very different results? I don't think. Agglomerative, keep on using agglomerative, not a problem. From a theory standpoint, I've told you, so that, I mean, if you go somewhere and somebody discusses it, it doesn't happen, you don't know, right? So the solution, the actual solution should lie between 1 and n. Now this is easier said than done, because this guy, this dendrogram doesn't guide me into anything. He says I've given you a, and this is also known as the merging scheme. This is the merging scheme because this is merging. So this is just giving me a merging scheme, but is not telling me what is my solution. So I have to figure out. So I'll have to figure out. I'm again saying that I have to figure out what is the cluster solution that I want. Now, how is that done? Now, you may say this is not science. Yes, that's the problem I told you. I told you in the beginning, cluster is not entirely science. It's science backed by art. There is a lot of art there. That's why you have to become an artist, and you become an artist when you practice. So clustering, very important. Please practice. That is a subjective thing. So how do I decide the number of clusters? I'll always remember in clustering, I'll always say lesser the better. The lesser number of clusters I have, the lesser number of clusters I have, the better it is. So that means I'll always take a top down approach because I want lesser than the better. At the bottom, I have more clusters. At the upper side, I have lesser number of clusters. So lesser the better. Always remember in clustering. I'll always like to have lesser number of clusters. Think of a marketing manager. I mean, if you tell him there are 20 kinds of cluster group versus there are 5 kind of cluster groups, I mean, is it practical to have? So if you have 20 kinds of customers, then you'll have to roll out 20 programs, marketing programs. Think about it. Can you manage it? Rolling out is one aspect, but can you really manage that? Think of 5 types of customers. Rolling out campaigns, rolling out marketing programs becomes easy, isn't it? The management is easy. So that's why we say lesser the better. From practical application perspective, lesser the better. And how do we decide? So we say wherever we get a high jump, wherever the jump is bigger, we say that is the possible place where I can look for a solution. And how do I look for a solution? I start, imagine that I'm moving my finger from right to left. Let's say this is the bigger jump. I cut one line, I move here, I'm cutting another line. So how many lines have I cut? 2 lines. And technically, this is known as a cut. Always, all this comes from this hierarchical diagrams come from graph theory, right? So decision tree or anything, the way this is put, this comes from graph theory. So if you the cut kind, this is known as a cut set. This is known as a cut set, and the way like I did this is known as cutting. So I've actually the word comes from graph theory. So I put a cut here, and how many clusters I should have? Actually, two. So hierarchy clustering, this is how I'll figure out the number of clusters. Now you may say this is too much of art. I mean, and initially when you are trying to, let's say when you see somebody tossing 3 balls at the same time and handling it, looks easy when you look at it. But when somebody actually gives you 3 balls and you try to handle it, there can be a lot of mess out there. So is there some help available? I mean, or is it I have to start tossing the 3 balls right from the word go? No, there is help available. That's a good thing, right? But this is how we have to do it, right? This is how we'll do it. We'll have to start with a tentative place, right? So the clustering algorithms, K means I told you is partitioning or K medioids or partitioning algorithm. There is hierarchical clustering. Then there is graph based clustering also. We are not getting into it. Then there is a model based clustering. So there are 4 or 5 kinds of clustering. But that's why I said there are 200 kinds of clustering. Also there is a change in philosophy also. There is a fuzzy algorithm also available. That's available in the cluster package that we are doing. So fuzzy cluster is available there. So if you look at a fuzzy cluster, and then there are clustering algorithms which are available because the size of the data becomes big. Example, Clara. Clara is an algorithm which is a k-means only, but works well when you have a large data set, right? Clara, then DB scan, these are or a rock, and so there are so many birds, there are so many algorithms which are there. Now talking about the fuzzy thing, whenever clustering, the basic belief is that your object will only belong to one group. That means the cluster membership is unique. As an object, it can either belong to cluster 1 or cluster 2 or cluster 3. Only one cluster. Clustering membership. I call it clustering membership, right? Or this is not only I call it, it's a universal thing. So it's clustering. The cluster membership is unique. right? The cluster membership is unique. So if the cluster membership, that means that it can only be one object can only belong to one cluster. The fuzzy approach says that the object can have multiple memberships. So let's say there are three clusters and there is an object. So the object number one may believe 70% to cluster number one, 20% to cluster number two, and 10% to cluster number three. Because this is the probability, it has to sum to 100, right? Isn't it? So the probability has to sum to 1 or 100. That's very important. So the fuzzy thing, there are no unique cluster memberships, but there is a probability. Now, when you hear to this idea, this is a wonderful idea, isn't it? Because actually that's the truth, that there is no pure membership at times. If you are working on a very messy data, you can't have a clear, you can't force a system to say, no, no, only belong to one, isn't it? All of us, if you look at it, do we have just, I mean, generally, if you look at Indians, that's the problem. We live in a fuzzy state. We are not Indians, right? We are Indians also, then we are Kannadis also, and Hindis also, and so many things. We are so many things, isn't it? So we belong to so many clusters, and we are fuzzy everywhere. And those probabilities are very difficult to estimate also. That's the worst thing. So fuzzy is this kind of idea, fuzzy thing is good to listen, good to, but to use it in the first cut, I'll advise please don't go for it. Can be very tricky, right? But I'm not saying that don't use it at all, but just use it for practice. Don't take it too seriously that, okay, based on this, I'll provide some kind of a solution. Providing a solution may absolutely become a very difficult thing, right? So out of this, what are we going to discuss? We are going to discuss k-means and hierarchical, graph-based and model-based clustering. I'm going to postpone for later on because what will happen is in model-based, when we do model-based clustering, then it requires some higher-end concepts, like example entropy maximization, EM thing. So there you'll have to understand what is entropy, and then you'll have to understand maximization. So there are a lot of things that we have to understand before actually understanding a model-based cluster, right? So we'll restrict ourselves to k-means and hierarchical thing, right? So how does the k-means? So the first algorithm that we are discussing. So we are now coming to the specific algorithm. How does the k-means algorithm actually work, right? So this we are showing it by a illustration, right? So how does the k-means actually work? Very interesting, very simple. As I said, not very difficult to understand. But if you don't understand it, just stop me and ask me. So I'm taking you through a k-means kind of illustration. I think I have made it full screen, and you can see that there are three kind of groups here. Those are represented by three colors. There is a light green color, there is a dark blue, and there is a brown color. The top of this portion where like I'm hovering my this cursor, this is the brown color, and this is the dark blue, navy blue kind of a thing. They all is navy blue, and this is the green thing. So what I'm trying to show you, and let's say this data is two-dimensional because we cannot show it more than that. So that's why we are assuming the data is these many points which are shown here, and it has just two dimensions. And what those two dimensions are, x and y, and this seems to be a standardized data because the values are lying between 0 and 3 and something minus 2 and 2, right? Should be a standardized data. So how does the k-means work? K-means means you have to supply and tell the system that I want three clusters because of your previous knowledge or whatever, or your client has already told you, I just want three clusters. That's it. I mean, you forget about anything else. Just give me three clusters and I want to work only on those. Okay, either comes either previous thing or the requirement, whatever. I mean, can be anything. So you want to divide this whole thing into three groups, right? Three clusters. So how does the k-means start? Step number one is randomly it will select 3 points as the centers. Because if it is a group of clusters, you will have centers in that, isn't it? Centroids, you may call it, or centers, you may call it. Randomly, it will select three clusters. right? So you can see its selection of clusters is very, very near. Ideally, this should have been first point. It would have selected this point here, and it would have selected the first point here. So how does the k-means start? Randomly, absolutely randomly, it generates three random numbers, and whatever those, and they can be neighbors also. Those 3 points can be neighbors also, right? It can be to that extreme. It picks up 3 points. K is what we have already given to the system. We are given three. That is why it is selecting 3 points. Had it been given 4, it would have selected 4 points, right? So K means we are the suppliers, 3 here. So that the first iteration, what has it done? It's iteration 2 mistakenly written, but okay, would I miss the first? This is the first iteration. So you can see here it is the 3 close points it has done. Now what will it do? From every center, it will calculate all the distances. So it will calculate the distance from all the points to this, from this center, from this center. So three centers and all possible distances. So this is a computation, though the calculations are simple, but it is a computation intensive algorithm. You can see it, right? It is calculating so many distances. Let's say if this would have been 1 million points, and if you would have given it 3 points, k equal to 3, it would have done 3 million calculations, isn't it? So in iteration 2, what is going to happen is it suddenly it finds, so it will find a group of this. So the iteration 1, what has happened is, let me write it for you. So C1, sorry, C1 is the first center. It will, let's say, have n points which are nearer to it compared to C2 is the second center, C3 is the second center. These are absolute thing. So there would be n points which are near to C1. Let's say p points in C2 and let's say m points in C3, right? They are nearest to C3. Now, when you have these endpoints, you will calculate a centroid of this, isn't it? Centroid is the center of the groups that you have. So that means a new center will emerge. You may call it like C11 this time, and this will similarly result into a new centroid. And you call it, this is because I'm saying, because this is a result of iteration number 1. So 2 has morphed into C21, and C3 will then become C31. This is what you see here. So these are the new centroid positions, 1, 2, 3. Are you seeing it's moving towards the reality? Though we had started with very close, now you can see it's moving towards the reality automatically. So iteration 2, something had happened. Let me go to the iteration 2. Iteration 2, like you can see, there is iteration 2. See, compare iteration 1. See, these are so close. Iteration number 2, they have gone a bit far. Iteration number 3, they are at the actual position, right? They are the actual position, right? So in very few iterations of iteration 5, you can see iteration 6, you can see it. In very less iterations, it's able to give you a solution. So you can see it here. See the centroids, right? Started becoming far, and then actually they say that this is the first group, this is the second group, this is the third group. But if you look at the original solution, this is how it was defining, right? So it says these are the natural clusters here. Okay, so K means this is how the iterations happen. It's very, very simple. Original thing, it will decide, calculate the distances, recalculate the centroids. It will keep on recalculating till the time there would be a point where this recalculation will not result into nearest points, right? Or you can have optimization method where you say that if you don't find more than 5 new points which are closer, then stop the algorithm. So it's going to stop. So this iteration are stopped based on very primitive kind of let's say optimization algorithm. A very simple optimization algorithm is required. You don't require a very complicated optimization algorithm. Okay. So this is how it stops, right? So strengths are, it will always converges to a local optimum. It always converges. It will not say that, oh, I am not not being able to converge, because the convergence criteria is very, very simple, isn't it? What you are saying is that if you don't find 5 new points, just stop, right? It's a very simple criteria, as I said. So whenever your optimization technique is simple, then the guarantee to converge is high. If your optimization technique is exotic, then there may be chances that the thing may not actually converge. Converge means that it stops, it finds a local optimum, local minimum or a local maximum. That's what convergence means, right? So K means this is how it happens. You can actually look at it. These are the data. And let's say absolutely you have taken these neighbors as the initial starting point, right? Let's say you want to divide them into three. So and this data you can actually try. If you want, you can try the data. And after the first iteration, you will see the mean squared error is 9, right? The mean squared error is 9. So now what will happen? The centroids are calculated again. And then the mean squared error becomes 1.78, right? After the second iteration, it has actually increased, isn't it? And at the third iteration, when the objective stops, you can see the MSE, the mean squared error, which can be taken as one of the parameters for the cohesiveness of the clusters. MSE is only zero point 0.3, right? You always want your MSE to be as low as possible. It's a badness of it. Mean squared errors, right? So these are your mean squared errors, right? Now, so this is your k-means clustering. And k-means clustering, because as I said, this is a machine learning thing, so there would be a complexity. So what is the complexity? Complexity is denoted by number of points multiplied by k multiplied by number of iterations and number of attributes. So if you increase anything, the complexity increases. Then you'll require a different kind of a system to actually tackle this, right? So for every algorithm, complexity and time taken is always calculated, right? We'll not get into it how it is calculated. So if you read there is a subject by the name of algorithms, right? There's a course also offered, I think, on Coursera. There is a course offered by the name of algorithms. So if you go into algorithm, you will see one of it is like how do you calculate complexity, calculation efforts, and all those things, right? So there the complexity is n into k into I into d. So if anything out of these four things increases, our complexity increases, right? The solution complexity increases, right? So at times it can be suboptimal clustering also. So all that is there. Whenever you are providing some solution, there is a chance that you might have some suboptimal solution also. And that's our biggest fear. How do we know we are not proposing a suboptimal solution, right? That's the entire game. And finally, as I said, you calculate something known as MSE or SSE to understand the quality of clustering, right? So we'll stop at K means, right? The hierarchical business will start tomorrow. Otherwise, it will become this thing. But tomorrow, like probably, if it would be good if you can discuss some part of something on regression that you have done. If you're facing any problems, that would be good. And there is still some homework if you can read about these distance types. What is a Gower thing? What is a Gower, as I said, is important. Levenstein is important. So at least Gower, Levenstein, know about this. That will help you. Okay. So read about it, or edit distance if you have time. If you are interested, you can read about it. Okay. So that's all for today. If you have some questions, you can ask me. Otherwise, tomorrow, like the agenda is, we'll go to hierarchical quickly, 5-10 minutes. We'll finish the theory of hierarchical, and then we'll go to the code straight away. A lot of codes. I got these codes. These codes are very extensive because there is a book which is now published actually, which got published this year, early half of this year. And how I got access to this codes is this professor had actually, when he was writing the book, so he had sent me a copy of this to review, asking my views on that. And this is how at that point of a time, I got these codes. Now this book is also available. Of course, I have a copy because it was sent like a complimentary thing to me. So if you want, I can share it. I don't know I can share it or not, but I'll share it believing that you will keep it only to yourself. You will not start sharing it further, right? So I'll share that. So all the codes would be there. It's one of the best books on clustering, and it is good because it combines R and clustering both together, right? So a good book, and this is what is there. Okay.